9.3 Miscellaneous Diode Applications. There are many practical applications for diodes beyond power supply. Some of these applications include clipper circuits that serve to protect circuits from damage as a result of overvoltage conditions. Clippers are common in computer circuits. And your text has a number of samples of clipper circuits. The image that one of the images, or several of the images, actually weren't very suitable, so I created some new ones. And so here we have a basic clipper circuit. This has got more detail than the ones in your text, but that will be fine. What this is a clipper from electronics workbench, and then this is the associated wave shape that it generates. We come in with a 10 volt RMS signal, and we usually evaluate this in terms of peaks, so we would divide that by 0.707, and this will result in a AC waveform with a peak value of 14.1 volts. And if you look on our oscilloscope here, you'll see number 1 here. This is in fact 14.1 volts. Now, what's going to happen in this circuit is that here we have a diode placed in this circuit, and notice the diode is going to be to forward bias this. We're going to have a value more negative than this biasing voltage that we have here. Now we've placed a 5 volt supply here, so we've got plus 5 volts, and in order for this diode to turn on, the cathode is going to have to be more negative than the anode. So in this case, that value is going to be about 4.3 volts. So this signal, this AC signal, comes in, and when it gets at about 4.3 volts, something is going to happen. This diode is going to turn on, and then the rest of that signal is going to be shunted down here to ground, and we will see we'll just see the 4.3 volts across this diode and this power supply. And so here is the resultant wave shape. So we come in with positive, and the original shape, if I was to draw this, and let's see if I can be a little bit of an artist here and draw the original, okay, it's kind of like that, but that would be the original AC input, and you'll see that this is performing a clipping action, and it's performing that clipping action at positive 4.3 volts, and due to this diode and power supply, you can see why did it clip it right there. In fact, on our simulation here, the value shows 4.270, which is very close to 4.3. Okay, our next clipper, we've got almost the same circuit. The diode is in the same position. The major change is that the 5 volts down here has been changed so that it's upside down. So now this is a negative 5 volts. And so the input remains the same. Everything remains the same except for this. Now, in this case, the diode, notice it needs to be, in order for this diode to turn on, it has got to be more negative than the anode. Now, in this case, the anode is minus 5 volts. So in order for this to turn on, this will have to be at least minus 5.7 volts. And so what you'll see in the associated wave shape, we have our positive signal coming in, and the diode is not turned on until we get down here to, in this case, minus 5.71 volts, and then suddenly the diode turns on, and now the rest of this wave shape, we're just going to see the 0.7 and the minus 5 volts potential across, and the bottom of this wave shape is essentially clipped off, and the original signal would look kind of like, let's see if we put it in kind of like that. But we essentially clipped off everything from minus 5.7 and below. Then this is a combination clipper. In this case, we have placed the, again, we're using the minus 5 volts, the positive 5 volts. In this case, we flipped one of those diodes over, so now it's going to be positive to negative here, and we have positive to negative here. There's no opposition here. Here we go positive to negative and positive to negative. And so in this case, we're going to have our clipping action here at minus 5.7 volts, and the clipping action here will be 5 plus the 0.7. It'll be plus 5.7. And so if you look at this signal, this sine wave, you'll see that it's clipped off. At T1 it is 5.7, and at T2 again it is 5.7. And the original wave shape looked kind of like that. And so this is a combination clipper. Okay, industrial applications of a clipper. Protection from high voltage input, and this comes right out of your textbook. This is the simulation here. We have a voltage from a transducer. This is going to be some industrial device that's feeding a input into a analog to digital computer that will be used by computer circuits. And sometimes these voltages can get kind of out of control and large, and so what we're using the clipper for here is to ensure that they will not go above 5.7 volts, because we do not want to damage the circuitry in our analog to digital converter. So here we have the diode here. This would turn on at 0.7, so a positive 5 here. So this would limit the input to 5.7 volts. Anything above 5.7 volts is simply going to be eliminated, and that will serve to protect our analog to digital converter. Okay, here we have, this is, let's see, isolation diodes are used to isolate various sections of circuits from another. An example of this is the battery backup for computer memory. Okay, so this circuit over here is a backup system for computer memory. Here we have the system. The system is operating here. It's providing 5 volts, and you'll see the polarity here across this diode would be like such. And so we have positive 5 on this side and ground here. So this is going to be forward biased, and we will have voltage coming here. Now, of note here, let's see. This is plus 5 here, so we'd have about 4.3 here. This diode has plus 3 volts right here. So in order for it to turn on, it's going to have a value less than what, 2.3 volts, something like that. It's going to have to be less than that. And the value there now is 4.3. So this diode will be reverse biased, and we will simply have effectively 4.3 volts is the voltage going to the memory circuits, and they will do their thing. Now, in the event that we lose power here, if power is lost, this will drop down to 0 volts, and now suddenly we are below 2.3, and now the backup system diode is able to forward bias, and so now we would be able to supply voltage to keep our memory circuits alive. So this is an example of isolation diodes are used to isolate various sections of circuits from one another. So the way these are configured, this diode is isolated from action until this one turns off, and then this one suddenly comes into play and keeps our memory from dumping. Okay, here we have diodes can be used to create an RC circuit that has different time constants for charge and discharge time. So here we have diodes that are used to establish one time constant for charging and another time constant for discharging. And by doing this, we could create kind of an odd wave shape. This principle is called asymmetrical time constants. And so let's see, how would this work? Here we have an input. Notice the input comes in 10 volts and then down to 0, and then 10 volts down to 0. Now, Let's see, here we would have 10 volts coming in. With that biasing, let's see, negative to this diode would be turned on by the 10 volts. Current would flow through R2, and we would have a charging action across C2. And the charging action would be a result of the time constant between R2 and C. And that charge wave would look, this is the charge wave right here, R2 and D2. Now, when this input voltage drops to 0, notice that we now have our cap is charged. It has a positive charge, and so now so this is effectively ground over here, and so now this diode will be cut off. We'll have a positive charge here, ground potential here. Now this diode is going to discharge. You're going to have this diode is going to conduct, and we're going to have a discharge pass through R1. Now we are experiencing the time constant, the discharge time constant set up by C, and the current that will flow through R1. So then we could have a very different curve as a result of that discharge constant. So this is another example of the use of diodes. In this case, we're creating an asymmetrical time constant. Our final look at diodes will be using them in something we call an AM detector. Now let's see, what have I got here. Diodes can also be used as AM detector circuits. Now that's for amplitude modulation in radio receivers. And we've got a nice simulation of this, and we're going to go to that after we discuss this. Okay, first of all, we're talking about an AM radio receiver. So let's see, what are we going to do? We start out with, first of all, to have an AM receiver, first of all, we have to have an AM transmitter, because we can't receive unless something is being transmitted. So first of all, we have information, and the information typically is music or voice, and those will be at a relatively low frequency modulating signal. Okay, so that's, voice, music, etc., data. Now, that is, in order to send that over the airwaves, we have to mix it with a high frequency carrier, and that's going to be, if it was 950 AM, that'd be 950 kilohertz. So here we would have the high frequency carrier. Now, here we have amplitude modulation circuit. This is where you have the mixing of this high frequency with the low frequency signal. And the resultant wave looks kind of like this. Here we have the high frequency carrier, and then riding on it is the actual information. This could be the voice, the music, whatever. And so that is transmitted out at a high frequency, well above your human ear's ability to hear. But it is at these high frequencies, these kinds of transmissions can travel many miles, whereas if it was transmitted at a low frequency like this, it wouldn't go very far. Okay, so it's transmitted out, and then down here we are at the receiving antenna. The antenna receives this modulated signal, and then it's fed to the AM detector. And I'm going to switch now over to another recording, and we're going to look at the AM detector with electronics workbench. Okay, we are in Multisim, and we're looking at the simulation of a simple AM detector circuit. This is in the circuits that came with your text. It is titled Figure 09_26.MSM, so I encourage you to run this simulation. Okay, first of all, let's see. We have an AM modulated signal here. In the previous screen, we had discussed how an AM transmitter and receiver, the basic blocks of how that works. And so what we want to do is connect channel A to the to look at the originating signal, and then channel B, we want to be able to look at the recovered signal. And we're going to connect a ground in here, and this will serve as a ground for A and B. So let's turn this circuit on, look at the output, and then we will talk about it. Okay, so here's our oscilloscope. I need to turn the circuit on, and then here we have our waveforms. Now the first waveform here, this is coming from our AM signal source. This would be, in essence, the transmitted signal coming from our AM signal source. And then over here, we're looking at, in orange here, this is the recovered signal. And you can see the relationship that the recovered signal is the same shape as the outside of the AM envelope. Now let's look at what's actually happening in this circuit. First of all, we come in with our, let's see, I don't know if you can see, okay, now you can see that. We come in with our AM modulated signal. The first thing that it hits is this diode, and the diode in this case serves as rectification. And so since this is, the biasing here would be positive to negative, this would pass the positive, or the part of this wave shape that's above 0 volts. So we would essentially pass the positive half of this wave envelope. Then we would go over here, and C1 and C2 are going to act as filters. And remember that when we looked at the rectifiers with DC power supplies, we had capacitors in there that smoothed out the AC. Now, the trick in setting these up is that we want to smooth out the AC in this modula, in the RF portion of this, but we do not want to do it so much that we smooth out the signal that is our recovered signal. So the time constants for the two-stage filter network must be short relative to the original modulating signal, but long relative to the high-frequency carrier signal. And so that is the simulation of a simple AM detector. We have our modulated signal coming in, and we have our recovered signal coming out. And so this particular signal, we would feed it into an amplifier and to speakers, and then we would be able to listen to the voice, music, or data, or whatever that was transmitted from the AM transmitter.